multi-agent seminar. It's a pleasure today to welcome SophieHall, who's a PhD student finishing her PhD this year from the Automatic Control Group in Electrical Engineering at ETH Zurich. She works directly with Professor Florian Dörfler. And Sophie's work is, I think, of particular interest to the topics that we cover in this seminar, as she focuses on multi-agent systems, generalized Nash equilibria, concepts of Nash equilibria, convergence of multi-agent systems to these equilibria. And she's done quite a bit of work in the theory of multi-agent systems and Nash equilibria, which she's going to focus on today. But she's also worked closely in two different applications. One is in energy systems, and this is particularly interesting in Switzerland, as I understand, because there's kind of more flexibility than we currently have in California for defining aggregates of residential groups or maybe businesses and residential groups in order to group together energy users and then basically apply as a block for certain benefits from the DSO. And so Sophie's working on that. She's also working on an application which is driven by agriculture in groundwater systems. And again, this is a really big deal in farming. Sophie works with some group in actually the Midwest of the U.S. But we have this big deal in California about farming and the use of water and where wells are and how you incentivize farmers to use water in different ways and the physical constraints of that. So welcome, Sophie. It's great that you're here.
Yeah, thank you for the invite and thank you for having me. So, yeah, I did my PhD on Receding Horizon Games, or a big chunk of that, or you might call it Game-theoretic MPC, and I'm going to talk about system theory, learning, equilibria, and applications. So let me motivate this from let me start, actually. We have a big workshop coming up at CDC about anyone here is joining the CDC, where we actually join forces with speakers from, the MPC side. We have Frank Algebert joining, we have Tamaya Bashar from the games side joining. We'll actually be talking more about learning in games, and then we have algorithms people. So Alberto Vemper worked on GNE algorithms, and we still have 2 spots for spotlight presentations. So if anyone, I thought this was a great audience. If any one of you has some very recent results that you'd like to present at CDC in our workshop, then send me an email. It's pretty flexible format.
Are you meeting with Negar today when you're here?
So she's traveling.
Oh, she's.
So we were supposed to meet, but she's giving a talk somewhere else, actually. Yeah. But we work together actually with Florian in the audience.
Oh, okay. That's good.
Yeah, so now let me jump into the topic. I would say that we now are realizing that we live in a world of finite resources, and ever more of those resources actually being allocated in an automated fashion. And that kind of means, practically speaking, that controllers will decide who gets how much of a certain resource at any given time. And now if I talk about resources, I actually mean that in a very broad sense. So I think many applications can actually be framed as dynamic resource allocation problems. So for instance, in infrastructure, you can see that a road is a resource. So who, as a user or driver, gets to use that road at any time? Then you have applications in bioresources, who gets to use water, so groundwater, as Claire mentioned, and pump water at a given time, and how much are people able to pump? And of course, you have robotics applications where you can now define resources, for example, airspace, or with drones, like who's allowed to pass a gate or some space first. And I would argue that many of these problems that we call dynamic resource allocation problems, they have certain ingredients that are defined by everyone wanting the resource, but people having heterogeneous needs. So you have multiple users accessing it, but they have conflicting objectives. Then the resource inherently is limited, road space is limited, the power that can go through a line is limited. So we actually have coupling and a physical constraint of users using the infrastructure that connects them. And then these systems actually inherently follow dynamics. So either it is engineering dynamics, for example, in infrastructure, it's actually dynamics that we built, or in the power grid, it's very like electrical, like physical dynamics, but also in natural systems, like in groundwater, we know from hydrology how groundwater dynamics evolve. And then we ideally, of course, would like to take actions right now that take into account future evolution of those dynamics and that are optimal in a sense of avoiding depletion in the future, also avoiding infrastructure harm. And I would say that the first top 2 points of that are actually very typical game theoretical concepts of conflicting objectives or constraints. And then the bottom two are actually very standard ingredients of an MPC controller or model predictive control policies. So in my PhD, I actually worked on combining these two paradigms to tackle these problems of dynamic resource allocation problems in a framework that's called Receding Horizon Game or Game-theoretic MPC. And that's what I'm going to talk about. And specifically, when I started my PhD, we actually noticed that there were already papers out there using game-theoretic MPC. So for example, for demand-side management, for electric load scheduling, and autonomous driving, and drone racing. So people apply concepts of like Nash over a receding horizon in applications, but we noticed as well that there was very little theory that existed to characterize the convergence of them and the type of closed loop properties that you would normally expect to have guarantees for in MPC. I mean, MPC theory really was developed over 40 or 50 years, since actually the 60s and 70s, to understand how do MPC controllers interact with disturbances in closed loop. So then over the course of my PhD, so the last 4.5 years, I actually spent looking into system theory aspects of this game theoretic MPC schemes, closed loop stability guarantees, fairness and social welfare. So especially in some of these dynamic resource allocation problems, we would argue in water or energy that they're very sensitive to social welfare questions and social justice questions. And I worked on explicit GNE seeking algorithms in the last year, and also on the application side, as Claire introduced, on energy management and groundwater management. But today, for this talk, I'm actually going to focus on these top three. So I'll do the system theory and the closed loop stability and the applications. For the other two topics, feel free to reach out to me. I'm here during the day, and I'm going to talk about it more. Yeah, so let's dive into the control scheme in itself and give a high-level overview of how this controller works and how it compares to existing methods. So I was like, I'm very much in touch with actually the German MPC community. So I don't know if people here are familiar with like Frank Algerber and these people, but they really want to understand when you introduce a new concept in the lines of MPC, like why why do you need a new perspective? Because MPC actually has been implemented for multi-agent system and distributed systems, right? It's a fair question. And to answer that, I want to give a bit of an overview of the different MPC paradigms that exist. So MPC was actually developed in the 60s and 70s in the chemical and automotive industry, mostly for very slow timescales. And it was usually a centralized optimization problem with one objective function, one optimization problem, and you solved it centrally. Then over the years, the issue was that these problems became actually very, very large, and then you had to split computation. So that's where then they developed distributed MPC methods so that you could solve much larger problems, but also have MPC controllers that interact at different parts of the infrastructure. And that then was actually still using one higher level objective, but then normally you designed it such that you could split it into different sub-objectives. And that would then result in M optimization problems, but they would be communicating. And the very famous examples are mobile robot coordination or sensor coverage, microgrids, where these distributed MPC schemes were used. And now I'd say, why am I introducing the game theoretic perspective, is that actually distributed MPC now, even in the last years, has made its way into applications where I think it's not reasonable anymore to assume that these objectives can be actually consolidated in one higher level objective function. And that's why I'm using the game theoretic perspective, because actually I would argue that in many of these applications of resource allocation, right, if you have multiple drivers on a road, it's not like these drivers inherently, they have their own local objectives, but you can't just sum them or combine them in one other function that would make sure that these people are happy. So then you cannot just have one optimization problem in the background that is solved by distributed computation, but you actually need to fully deal with that heterogeneity of these conflicting objectives. And most importantly, right, in games, we know that a Nash equilibrium or and game-theoretic equilibrium does not necessarily coincide with the minimizer of an optimization problem. So it's really a different point that we're optimizing for. And yeah, these heterogeneous objectives then would actually lead to a generalized game. You have distributed computation, and the right now rather famous applications are autonomous driving and racing and these resource allocation problems. So that's what I'm going to focus on. And I'm just going to go quickly over what are the sources of coupling that exist in these games.
So that, is there a way to remove those, like that okay thing, and then maybe that one, if you go to more, and then you just go to hide
loading media.
Yeah, that one, Great. Okay, perfect. Thank you, Sophie.
So we can have three sources of coupling that typically arise in these type of applications. So you could have coupling in the dynamics, for instance, in groundwater, that's very clear. Hydrological dynamics, they are coupled. If you draw water out of there, it'll affect the water state of someone else as well. You have you have coupled stage costs. That's because the cost of, for example, extraction of a resource depends on how much else everyone else is extracting. And you may have coupling constraints. So that is the classic thing of, well, the road, we have collision constraints that affect each other's actions at every time step. And then I would say this is, of course, the general framework. Depending on your application, you can kind of mix and match which ones apply. And then you can actually write down these game-theoretic MPC problems in a similar way as in an MPC fashion, where you have your typical ingredients of a stage cost, the dynamics, constraints. Notice here the standard game-theoretic notation of UV being the action of agent V and U minus V the action of agent minus V. And here it's the general coupled case where they actually have coupled dynamics. And then you have an initial condition which parameterizes your game. And instead of now solving this as an optimization problem, this actually constitutes a generalized Nash equilibrium problem, exactly because of these couplings in the stage cost, the constraints, and the dynamics. And then the idea in game-theoretic MPC is actually to apply, rather than having in classic MPC and a dynamic system, a feedback with an optimization problem, which parameterizes your feedback policy. You now actually have this dynamic system and feedback with this generalized constraint game. And that constraint game actually then is constituting your feedback policy, which then is parameterized as well in your initial state. And you run this in a receding horizon fashion.
So Sophie, can I ask a quick question?
Yes.
So on your previous slide, when you had the setup, so here it seems the constraint is on per stage control. Can it also incorporate like constraint on like a trajectory wise control?
Yeah, so you mean if this could be also over entire trajectories, the dynamic constraint?
Right.
Yeah, I could also formulate it over trajectories.
Okay.
That depends a bit on, of course, saying depends on what, if your dynamics are super nonlinear, if you can still solve it. So that's more on the solving side of things, that there is a bit of issues on the algorithmic side of solving highly nonlinear GNE problems. But yeah, formulating you can, yeah. Yeah, and then I guess the difference here being, why is it theoretically interesting and difficult to deal with? Because right now, instead of this optimization problem here in feedback, you actually have this generalized game, which are effectively you have, if you have M agents, M coupled optimal control problems that you're dealing with. So the nature of how they evolve in a receding horizon fashion is different to an optimization problem. And let me dive into the solution concept, like generalized Nash equilibria, a little bit. Just to give you context. So of course, now that we're not dealing with an optimization problem anymore, but we're still wanting to apply something in a receding horizon fashion, we need some fixed point concept of these generalized games. And those are actually generalized Nash equilibria. And for this part of the slides, I'm just going to use a simplified notation to make the slides a bit more readable, but it actually applies to the general version as well. So we said that a joint decision U star is a generalized Nash equilibrium if for all agents it holds that no agents want to unilaterally change the decision because they cannot change their cost any further. So this is the typical Nash condition. But then on top, where the generalized comes from is actually that you have coupling in the action set. So now actually my action depends on the optimal actions of other agents. So U minus V star. And now you can solve these for a generalized Nash equilibrium problem looking at two different perspectives. The first one would be looking at the KKT system. So here you have the gradient of JV, so the cost function of agent V with respect to their own decision, and you have the dualization of the shared constraints GV, and the complementarity conditions, of course, so on and so forth. But secondly, you could also look at the reformulate it as a quasi-variational inequality, where here now it is a variational inequality, but actually because we have action sets depending on each other, we now have it moving in space. So it's like a variational inequality that moves in space. And one of the major issues with GNEs in general is that actually the set of GNEs is large, it is possibly infinite, and it is very hard to solve for. So to this date, there exists no algorithm that can solve for the entire set of GNEs. So there exist algorithms that can find you one specific one, but not the entire set. And as I said, there are usually infinite amounts of solutions. So that what people normally do to simplify things is you select one specific one out of that set and you implement that one. And anyways, in real-time control, right, we need one control action to be applied to our system. So having a solution set of infinite solutions isn't very useful. So the standard one that people actually select is the one where the Lagrange multiplier lambda star is now homogeneous across all agents. And why do people do that? There are two reasons. I would say one, it has a really nice practical interpretation. Now lambda star is actually a set of prices for which there's no advantage for any of the agents to being allowed to pay for constraint violations, because we know from Lagrange theory that actually it's the penalty that at which everyone is not incentivized further to wanting to pay more for the resource, because it balances out basically the gradient of an individual agent's constraint, objective function, with the gradient of their constraint. And in the application, that's also kind of nice, because in energy, for example, would mean that it is the shared shadow price that everyone is paying to adhere, for example, to power line limits. And why it's also nice from a theoretical perspective is that you can actually now reformulate your GNE problem as a variational inequality and not go away from quasi-variational inequalities. And actually, VIs are a lot better understood from applied math perspective, and there are a lot more algorithms to solve for VI solutions. And this is a bit of a summary, but these variation GNEs really have been used in a wide variety of applications. So optical networks, wireless communication supply chains, autonomous driving, it's really quite many. Me, myself, as I said, work on energy management. So that's what I'm going to focus on at the end, but it is quite a widely used solution concept. And now I'm going to dive into the system theory aspect of these equilibria. I think now is a good time to, if someone had another question, to stop for a minute. Otherwise.
Hi, Sophie, can I ask a quick question?
Yes, sure.
Can you hear me? Yeah, I'm curious, now, do we mainly focus on the open loop setting when we solve this Receding Horizon game for the future?
So now this part of the talk is going to be exactly about the open loop evolution of dynamic GNEs. And then the second part is going to be about the closed loop properties, so the closed loop.
I see. Okay, thanks.
That's Jim Sheeby.
Okay.
Yeah, he's working with David Friedrich Kyle
okay.
in Austin now. Yeah,
cool.
Hello.
Yeah, so that was a perfect, smooth transition. So exactly this part of the talk, we're going to look at the open loop finite horizon dynamic GNE, because actually over the course of my PhD, first I looked at closed loop analysis, but then I realized, even in optimal control, to understand closed loop properties of any system, you better understand well what they're doing in open loop, so that you know what they would converge to in open loop. And now let's look again at this GNE problem and the general setting. And now the question is, if agents compete in this resource allocation problem, what do they converge to over finite horizon and in open loop strategies? And actually, I want to take a step back, and that's how I started this project. So the question here is really like, now, if we have an initial condition and we have some black box trajectory generator that's basically giving us always an actuation and a state strategy, like what type of behaviors can we use in our simulation to then get system theoretic analysis, sort of system theoretic results out of that? And one thing I was realizing across all the simulations that I was running, independent of the application, that I often observed a certain type of phenomena. So this is, let's say, your initial condition of your system, and it converges to some operating region and then diverges again. And you see that in many of these games. And then I realized this is actually a phenomenon that's not only happening in these generalized Nash equilibria that I'm working on, but that's actually quite well known in optimal control. And this phenomenon actually has a name, and it's called the turnpike property, which I don't know if people here have heard of it, but it means the idea is that your optimal trajectory resides in a region, but towards the end of the horizon, it diverges again. And in optimal control, there are actually very simple ways of explaining why that happens. It happens whenever you do not have your, let's say, vanilla quadratic cost function anymore, but you have another type of cost function. And then, for instance, in energy applications, it is for a finite horizon controller optimal to, at the end of the horizon, not charge the battery anymore, and not buy energy from the grid anymore, but just to discharge the battery. So normally you would see that it stays around an operating point, the battery charge, but then towards the end of the horizon, you wouldn't want to buy energy from the battery anymore, but you just consume everything that's stored in the battery. So that is known in optimal control, and I was observing the same principle in these generalized Nash equilibria, so I was wondering if we can use some of the system theory that was developed in optimal control also for these games. So basically the question is, observing this in simulation, can we say something about the system and its attractor point here, so the point that these agents competitively converge to? And yes, you use the turnpike property, and that one, you can actually describe it through an entry arc, a turnpike arc. So this is the region where it stays around that attractor point, and then a leaving arc. And in mathematical terms, how the turnpike property is defined is actually, I'm going to give just the mathematical definition now. You kind of count the number of points of your open loop trajectory that it spans within an epsilon radius around that attractor point. So this is but the intuitive interpretation is what I said earlier, right? You look for, is your trajectory around some optimal operating point for a certain amount of time? And the nice thing is, from this turnpike property, you can then use a lot of system theoretic tools to say something more general about that point about your system. And as I said, actually, the same thing, I observed it in games. So now this is not any trajectory, as I said, but this is actually a trajectory resulting from your generalized Nash equilibrium problem. And the interesting thing is here, you really see that for different horizon lengths, you're going to stay around that attractor point for longer. So if you increase your horizon length, you will always stay around that optimal operating point for a longer time. And now the first question that I was actually wondering, is this point here, XS, what does it mean in the context of this generalized Nash equilibrium problem? And the interesting thing is the point that they converge to, or that region, isn't just any point, but it is actually the solution to your steady state generalized Nash equilibrium problem. So this is the one-step horizon problem, but with an additional steady state constraint. So as we see over here. So it kind of interestingly means that agents compete, but they learn how to converge to that steady state GNE without me giving them any information about that. So usually in MPC, what actually happens, right, you would have terminal ingredients with terminal sets or terminal penalties, but here you already see that they converge to that point. So, which is actually, it's a strategic equilibrium because it is still a generalized Nash equilibrium. So strategically, no agent would have an incentive to change their strategy. But on top of that, it is also a dynamic system equilibrium. And I think that's what makes this point special, that it is actually, right, a steady state of your dynamical system, and it is a strategic equilibrium point. So that's the excess, which is the solution to the problem above. And then the question that we were asking, can we actually formalize the convergence that we see in simulation to this point? Can we formalize it from a system theoretic perspective? And the answer is actually yes. So we have a theorem in the paper. Here I'm just going to be giving a short version, but suppose that XS that the turnpike property holds at that point for your generalized Nash equilibrium problem, then you can actually show that means that your system is strictly dissipative with respect to that point with a specific supply rate. And for people that are maybe not so familiar with dissipativity theory, it's actually a generalization of Lyapunov theory. So it actually tells you a lot about your system. If you know that your system is strictly dissipative, but it is generally really hard to prove it, it's kind of like asking, do we have a Lyapunov function? Where you kind of need to find the Lyapunov function. But this is a nice way of circumventing the path of, okay, do we have a storage function, which would usually be the corresponding question in dissipativity theory, but you actually can use this turnpike route for showing if we have this turnpike property, then we actually get strict dissipativity under some technical conditions. So in the paper, we have a proof in actually both directions. So one applies the other and the other implies, so forward, backward, basically. And then the next question that we were trying to answer about this point, XSUS, like the steady state equilibrium point, does that mean that this point is actually an optimal operating point in any sense, right? Because why would the population spend so much time around that point if it wasn't cost optimal in any sense, right? So that would be an optimization perspective on this game. And how do we define an optimal operation? So it would mean that no feasible other game trajectory can have a better asymptotic average performance than this point XSUS.
What does average mean here?
Average over infinite horizon. Yeah. So, and the answer is also yes, and we show that in the paper that if the system exhibits this turnpike property, then the steady state GNE is not only a strategic equilibrium, and it's not only a steady state of your dynamical system, but it also actually minimizes the sum of costs of the agents at that point, given that it is an equilibrium trajectory. And that's an important notion that I want to spend a little bit of time. So it doesn't mean that your steady state GNE minimizes sum of costs globally, right? Because we know that social welfare would be, the social welfare optimum would actually minimizing sum of costs. But what I'm saying here is out of the set of competitive equilibria, if you see that agents really compete, out of that set of solutions, it is the one that actually minimizes their sum of costs. So they actually find the point, or they learn to operate around the point where they're still in a competitive setting, but they also minimize sum of costs. And I think that's what's really interesting here. So in the end, we can actually show not only this connection between turnpike and strict dissipativity, but also optimal operation at the steady state GNE. And then I guess as a last question that we were wondering in this project is okay, why do agents then learn the steady state equilibrium but diverge from it again? So this intuition that I was giving you before, an optimal control of why do you have this leaving arc in the first place, right? You might think they should just stay there if they found it. And there it's interesting, you can actually look at the KKT conditions. And I'm gonna first write down these two problems. So you have what I introduced in the beginning, this finite horizon generalized Nash equilibrium problem. You have the steady state generalized Nash equilibrium, and this is a one-step problem with the steady state condition of your dynamical system. And now you can write the KKT conditions for both of these problems. And here you see actually that when you analyze it for this, so the steady state GNE to be a solution to the KKT system of the finite horizon GNE, so for the agents to wanting to stay there, we would actually need this system to satisfy all the KKT conditions of this GNE system. And right now, like this, you can actually, now actually, maybe it's a bit too fast, but you could plug in these conditions and actually see that it satisfies the KKT system above. So you would think in the first place, well, this is an equilibrium point of this KKT system above. But now what we've observed, the main reason why then they are still diverging, you don't see it here in these, in the optimality conditions, but where you do see it is actually in the boundary conditions of the problem. And now for simplicity here, I assume that at the boundary, there are no active inequality constraints, but you can also derive it for that case. What you see here is actually that in the finite horizon problem, you have a constraint on your dual variable at the terminal point. So at lambda n, you actually force lambda n to be 0. So that's why the steady state game is not a solution to your finite horizon GNE problem. And you actually see that in simulation, that the Lagrange multipliers, they converge to the lambda s, which would be the dual variable that corresponds to the solution XSUS, they converge to it, but then they diverge at the end of the horizon to 0. And this same mechanism is actually well known in optimal control, but now we've also shown that it exists in these games. And that is the reason of why they converge to the XSUS, so this optimal operating point, but actually through the KKT conditions, they are forced to diverge from it again at the end of the horizon here. And then, of course, you can ask, can we do something about it, like induce or change something about the problem to make them stay at that operating point? And the answer is actually yes. There's different ways of doing this, but here I'm going to present one of them. You can design a terminal penalty smartly to enforce that they converge and stay at that point. So here, this is the cost function, as I said, per agent, which is the sum of the horizon of the finite horizon problem of the stage costs. And if we want them to converge and remain at that point, we actually introduce a terminal penalty, which is lambda SV xn to the problem. And that means that now if we look again at the KKT conditions, we get that the boundary condition here now, lambda NV is lambda SV. So actually now, rather than forcing them to diverge from lambda S, you actually force them to converge to that and remain exactly at that dual variable.
What are you giving up to do that? I mean, obviously the flexibility, but what is the downside to do that?
I would say that, okay, the downside, and that's a discussion I've been having with many people, is it reasonable to introduce terminal ingredients into competitive settings? And that, I think, is a bit of a philosophical question. Like, you lose that maybe the agents, they don't want to play that game, right? Here in the beginning, if I say, okay, it's just a cost that they give me or a stage cost that they actually have privately as an information, then that would be a fully competitive setting. Then this would be me forcing them to care also about the long-term performance of the game. And then you would have them abide by that or not. Yes, that's but we can see quite nicely now, this is simulation results, that this would be the cost and the GNE open loop trajectories without that penalty. So you see what I said earlier, they converge to that point and they diverged quite heavily again at the end. But when we design this penalty, as I said, we actually see that you get exact convergence and they just remain. And that is super nice, because the good thing about this is also that usually you do not want to have exact terminal end constraints because they're numerically really difficult to deal with and they really decrease your feasibility region of your problem. But here, having a cost term that takes care of it is actually a lot milder on the problem numerically. And then another extension of the paper is that we can see that you can also learn this penalty. So you don't have to pre-compute it, you can learn it while operating your system iteratively. And that it still works very well that you get convergence to this point and remain there. Yeah, so this I think is a good point to stop shortly. So this is the big chunk of the talk. If anyone has a question right now about this. Okay, I guess this was the big part about system theory on dynamic generalized Nash equilibria. And I'm going to switch actually to the stability certificates. But here now this is a different setup because it was basically 2 different projects and 2 different papers. So this now is really looking at rather than the open loop properties, it looks at the full closed loop system. So again, this MPC style feedback between the dynamical system and the GNE strategy. And when I started my PhD, as I said, there were actually no stability certificates so far for any of these closed loop systems. So this is, to the best of my knowledge, the first paper that actually proved some stability certificates, but I would say under somewhat stringent assumptions. And I'm currently working on an extension which removes quite a number of those assumptions. But for now, the assumptions were actually that you have a stable LTI system, input constraints, and a stage cost, which is quadratic in the state, but can be anything in the input. And one might ask, okay, it's kind of stringent assumptions. Does that mean this is even relevant in application? But I was actually able to show in super simple, already 2-player settings that you can have stable LTI systems And if they're interconnected through the generalized Nash equilibrium, that they destabilize each other. And an interesting intuition behind that is, especially in aggregative games, where you have often the shared cost, for example, in energy, is like the shared aggregative usage of electricity. You can have it that in one time step, one agent charges their battery and the other one discharges, and then they just switch. So because then their aggregative cost is always zero. So that's the optimal thing actually for the shared agents to do. But the switching behavior actually, in then feedback with the dynamical system, really introduces instability. Yeah, so that was one of the motivations of working on this. And yeah, so we look again at this Receding Horizon Games problem, but what we spend a lot of time on in this project was actually reformulating it. So you have this compact form notation, and if you write it in a compact form, and use some GNE literature, you can actually write this as a generalized equation. So the solution to the compact form GNE setting here can be also formulated as a zero finding problem of an operator f ux and the normal cone nu at x. And here I'm going to take apart a little bit what is this operator here and why is it useful to reformulate it in that way. So actually fu here is the classic, I mean, people that are familiar with game theory, we have the pseudo gradient, which is always the stacked vector of agents' cost function with respect to their own decisions. So this is this object here. But now under the assumptions that I made in the beginning, the nice thing is you can actually split this into the part that depends on the input trajectories of agents and the part that depends on the initial condition of your MPC problem or your receding horizon problem. And this structure actually then allows you to reformulate it and analyze it theoretically very well. And these, now they look like small operators, but they're actually really large matrices or large operators. Because here you actually, I'm hiding basically the entire multi-step horizon problem in these operators down here. Yeah. And then if you write it like that and make some standing assumptions, so the most important one being the pseudo gradient being mu strongly monotone, and that is an assumption that is kind of the same as an optimization requiring that your problem is strongly convex. You can actually ensure that the feedback policy, so this variational GNE is unique, and that is important in stability analysis, because what you do not want, or that would be a lot more complex if you have a set of equilibria, then you might have it that from one point to the next, you're actually switching strategies, and you don't want that. So here, through these assumptions, we're ensuring that your feedback policy is unique. And then through this uniqueness, you can actually characterize the closed loop system through this zero finding problem of that generalized equation. And the most important thing is, because of the structure that I introduced earlier, we actually have now two systems. So on top, we have this LTI system, which I said was the dynamical system. But at the bottom, we now use this generalized equation, reformulate it, and we use this splitting of the component as a function of the input trajectory and the state, the initial condition, to formulate an operator phi. And using strong monotonicity, we can get co-coercivity. And the most important, after all this massaging, is that you can actually get now your GNE problems and the feedback between the linear system and your GNE. You can write it as in typical block diagram form. Most importantly, the feedback strategy is now a static nonlinearity, and you have knowledge about the static nonlinearity. Maybe some people here are familiar with dissipativity, incremental dissipativity, or some people also know this under Louret type problems. So we have dynamical systems and a feedback, you have a nonlinear static operator. And that is actually a nice structure to have. That's why we went through all this reformulation. And then through that structure, you can actually derive LMI conditions, which are very easy to numerically verify. So now we have certain parameters that are important. Mu here is actually the strong monotonicity constant of your pseudo gradient. And these are the operators that define also the pseudo gradient. And these are the matrices that define your linear system. And the nice thing is now with these LMI conditions, you can actually certify global asymptotic stability to an equilibrium point and recursive feasibility. And on top of that, in the specific case where you have decoupled dynamic systems, you can actually verify these LMI conditions locally. So that's even better, because the issue with LMIs and multi-agent systems is, of course, that most of the LMIs would scale with the number of agents. So you would have an LMI condition. You wouldn't want to have an LMI condition that is states times number of agents, because you can't compute that anymore. But now in this specific setting, which is actually very applicable to energy management, assume everyone has their own little battery system. You would have an LMI conditions that is decomposable. And the nice thing here is also then if agents verified locally, they can basically do plug and play. So you can join the game, and then the operator would kind of be, hey, if you want to join, you need first compute or see that your system parameters fit such that you can solve this LMI condition, and only then you're allowed to join.
This might, maybe you talked about extensions, but if you were to model your dynamics using some kind of switched LTI system, it seems like these conditions would still hold. One could generalize these conditions.
Yes, I think you can. The important part here is that these matrices, they actually have the also the input response and impulse response matrices over the entire horizon. And I think if they switch, they would change, right? So that's a bit
okay, yeah.
But yeah, I mean, so we did already look at an extension.
That comes in that nonlinear feedback, basically.
Yeah. So that is part of the nonlinear feedback. So I think you would still be able to do it if you. So the important property of the nonlinear feedback is that you remain co-corrosive. So as long as your switching does not mess with the strong monotonicity of your pseudogradient, I think that is really the fundamental property. As long as you can preserve strong monotonicity and your switching, I guess, you still remain LTA stable, then I think it should probably work. Yeah, and I guess now in the last couple minutes, we still have, I guess, yeah. In the last couple of minutes, I just want to go shortly over the applications that I was working on. So as Claire mentioned, I worked on energy management, groundwater, a little bit on electric vehicle charging, and I have one paper on actually supply chains. So supply chain competitions, which is a bit more the very competitive setting. But I want to focus on the energy management example. And here, the problem is really that, I mean, in Switzerland, but also in Europe in general, that we have more and more households that want to actually manage their energy optimal in some sense. So they install smart meters, and those smart meters which actually control your heat pumps or other appliances in your house. And the issue on an individual household level is actually that we see these huge peaks normally. So there's no electricity being used during most other hours of the day, but then there's big peaks at certain hours. And now if you look at an individual household perspective, you actually have different ingredients to this problem. You could have thermal control, EV charging, solar panel control, and battery charging, all being part of one of these smart homes. And what actually an individual agent would like to do is to charge and discharge their battery and shift sort of consumption of big appliances to reduce their electricity bill. But now the issue is you can't just do that on a single household level. And I think I mentioned that to Claire earlier, but I was working a bit with the Power Systems Lab, also at ETH, and they were trying to do smart energy management for individual households. And the problem is if you just implement an MPC controller on a per household level and you send prices, then those MPC controllers would shift consumption all to the same time. So you actually create peaks that didn't exist before if you don't do any coordination between households. Because everyone would try to do it smartly or at best price, but if everyone gets the same price, you will actually do exactly the opposite and strain the grid even more of what you wanted to do in the first place. So they call it rebound effects. So what you need to do is actually make sure that you take into account this coupling through the infrastructure and shift the peaks in a smart manner. So not just treat one individual household, but actually treat them jointly. And I think this game theoretic perspective is actually a very nice way of modeling that, because if you were to model actually this interaction, you can use it, you can explicitly take it into account. So saying that the energy price is actually a function of aggregate consumption. So this would make sure that they do not all switch to the same peak and you get a new peak, but actually aggregate pricing would then make sure that you flatten the peaks. So you can model that through, as I said, an energy price sigma that now depends on UV, so the energy consumption of one agent and the energy consumption of all other agents. And on top of that, if you wanted to enforce hard constraints, because of course grid infrastructure is very sensitive, you can't only do that through pricing, you also need a hard constraint on how much power is running through the lines that agents are coupled to at one joint coupling point. And then you can enforce that through this GNE mechanism, you can have this coupling constraint. And I actually have a project where now a student has a full-scale grid example, and we have real data from Switzerland, and it's actually checking now. You have different households connected to one bus, and you need to ensure at that bus you would satisfy certain power limits. And I mean, this is a smaller CDC paper that I'm currently working on the journal extension, but you can see that it works very nicely, that actually this energy management, so you reduce the peaks a lot through this receding horizon implementation, and it's also quite a lot better than just doing repeated open loops. So if you were just to apply your open loop sequence multiple times, that is also not optimal compared to doing it in receding horizon. Yeah, and the nice thing is that you can do very effective disturbance rejection, actually. So here we were dropping the joint load limit, so that's kind of the load that all agents aggregately are allowed to consume. We dropped it by 70%. And you see that agents, they shift consumption, but they're going to consume then more electricity later, of course, to make up for this consumption that they didn't consume during
When did they know that it was going to be shifted?
So here I give them the information 30 minutes. So it's in 2 time steps in advance. Yeah. And I guess here's going to be the conclusion. So I worked on Receding Horizon Games, and I guess today we focused on the system theoretical aspect. So we actually show that agents interact competitively, but they learn optimal policies, which are strategic equilibria, but also steady state of the physical system. And we can design terminal penalties which enforce that they remain at that optimal operating point. And I've shown closed loop stability certificates through LMI conditions, which can be verified in a distributed manner. Yeah, thank you very much. And I guess I'm open to questions.
I wanted to ask about the stability certificates and the recursive feasibility results, how that can be ensured with those conditions.
Yeah, that's a good question. So, and that's a detail that I was well, now in my new paper, we have full state constraints, but here actually we didn't have full state constraints. So recursive feasibility comes for free if you do not have state constraint. It was just we were asked to add that to the paper to make it clear that feasibility isn't an issue, because of course without state constraints it's never an issue. Does that answer? But wait for I think 1 or 2 months. I'm going to have the new preprint. So then you'll have the full answer there.
Yes, okay, I will keep an eye out for that. Thank you.
Any other questions?
Hi, Sophie. Thanks for the great talk. I have one question about the diagram which you had in the stability receding horizon games part, where you had like a k-step game that feeds into
this one?
The block diagram where the k-step game feeds into this operator which you had phi, I guess.
This one, maybe?
Yeah.
Yeah.
Right. So it looks like it's a static operator.
Yeah, this is a static map, but it's parameterized, of course, in your initial condition.
Right.
So the
do you think do you think it is of any use, or it will be better to have like more of a nonlinear or a dynamic updation which feeds back into your MPC controller, maybe in terms of performance, etc.?
Well, so this is still dynamic in the sense that I do have all the system dynamics in this operator. So you are predicting over the entire state and input trajectory of your dynamical system in this operator. That's why it was important that it is a linear system, because then I can all substitute the dynamics through their corresponding matrices. Is that in the direction of your question, or did you want to know something more?
Yeah, I was thinking more if there's some kind of hidden states in your you can have another dynamical systems composed with this initial LMI system.
So there is, of course, the At the moment, I was always talking about the dynamic system being in feedback with your GNE policy. So assuming that you have already converged to your GNE, but there would be another component of you could add another block down here where you say, what is the interaction of how do we converge to that GNE? And then you would have basically have 3 layers of an interaction between the algorithm solving for the GNE and your physical system. Yeah, so that is possible.
I see.
Does that answer the question?
Yeah, I was just asking if that may help in any way in terms of improving performance. So here, I think you are guaranteed a stability certificate.
If that helps, I'm not sure, but that could be investigated.
Okay.
Any other questions? All right, if not, let's thank Sophie again. Thank you, Sophie. That was a beautiful.
Thank you.
Okay.
Thanks, Sophie.
And Sophie.